In this segment, we need to talk about the common ion effect. The common ion effect is just an application of Le Chatelier's principle. And all it says is that when you're specifically talking about an insoluble salt, the solubility decreases when you have a common ion present. And this makes complete sense, right? If we increase the concentration of hydroxide, then this will shift the equilibrium to the left. Or another way of saying this is that the solubility of calcium hydroxide will decrease if we're in a solution that has hydroxide already present or a basic solution. So addition of hydroxide anions will shift the equilibrium to the left. And again, we can think about that in terms of the KSP. Remember, anytime your Q becomes greater than your KSP, which is what would happen if we added some of a common ion, then that's going to shift your equilibrium towards the solid and lower the solubility. So the actual equilibrium constant doesn't change, but the solubility of this particular insoluble salt will decrease if a common ion is present. This is just an example from the Silberberg textbook that some of you may have used for general chemistry, and it's just showing that for a particular example, lead chromate, if sodium chromate is added to a saturated solution of lead chromate, it provides this common ion, causing this insoluble salt to precipitate out of solution. Okay, so let's just go ahead and do an example problem. So we previously looked at the solubility of calcium hydroxide, and this was just in a regular aqueous solution, and we determined that the solubility was 1.2 times 10 to the negative second molar. So be thinking about that. So now we're going to do the exact same problem, except now we're predicting what the solubility of calcium nitrate will be in a 0.1 molar calcium. We're predicting what the solubility of calcium hydroxide will be in a 0.1 molar calcium nitrate solution. So the common ion here is calcium. So again, because we have calcium 2 plus ions present, this will shift the equilibrium to the left. So just like usual, we'll always write the equilibrium expression first. And our KSP. So initially, just like always, we have some blob of our solid. And in this case, we do have an initial concentration of our calcium. We have 0.1 molar calcium 2 plus, but no hydroxide present. And then our change is going to be just like we did previously. For every 1 mole of calcium hydroxide that dissolves, we're going to form 1 mole of calcium 2 plus and 2 moles of our hydroxide. So again, we could have written these as X's. So I'll just write that, as S's to indicate solubility. So at equilibrium, we ignore this. So we have 0.1 plus S and 2S. So when we write out our KSP expression, we're going to say our KSP is equal to 0.1 plus S times 2S squared. Okay, so now we need to talk about how to make good assumptions to simplify this, because you can see that this could be a little bit messy to solve. And so what we're going to talk about is how we can make an assumption to simplify it. And so what we can do is we can say that, okay, because this KSP is very small, that the amount of calcium hydroxide that's going to dissolve is going to be very little compared to our calcium nitrate concentration. So we're going to say that S is very, very small compared to our calcium concentration from the calcium nitrate. So we're going to just ignore this S. And so we'll rewrite this as 0.1 times 4S squared, or 0.4 times S squared is equal to 6.5 times 10 to the negative fifth. All right, so here's just showing a little bit cleaner way, but this is exactly what we did. Our initial concentration of calcium was 0.1. Our change was our solubility plus S plus 2S. At equilibrium, we had 0.1 plus S and 2S. And again, we said that S is very small compared to 0.1. So we end up with 4S squared equal to, and if we solve for our solubility, we now get 4 times 10 to the negative third molar. And remember back from the previous, so remember that it was 1.2 times 10 to the negative second molar in a regular aqueous solution. So the solubility has gone down significantly, almost by a factor of 10, due to our common ion being present. And you always want to check that assumption. So you want to make sure that this change is less than 5% of our initial concentration. So we can do that. 4.0 times 10 to the negative third divided by 0.1 times 100 is 4%, so that's less than 5. So that means we have a good assumption.